Hi. Um, in the first half of this unit, we are going to be studying a class of problems called multi-arm bandit problems. In this first lecture, I'll introduce the topic and also some of the mathematical preliminaries we need for the rest of the unit, for the rest of the first half. Let me share my screen. Okay, let's get started. So we begin by introducing the multi-arm bandit problem, and a good way is to start with a motivating example. So we have a patient who has to be assigned to one of several different clinical treatments. There are many possible treatments available, but we don't know which is the best one. But we want to make sure we assign the patient to the best one. So how can we do this if we don't know how good the different treatments are? Well, there's not much we can do if there's only one patient. All we can do is assign him or her at random. But more typically, we are in the situation where we have a large number of patients and over time, and we assign patients, observe what happens, and we can use that information to decide how to assign future patients. So that's the setting we are in. We have a large number of patients seeking treatment, and we have to sequentially make decisions as to which treatment to assign them to. And okay, for simplicity, let's assume that at the time we make a decision, we know about the outcomes of all the previous patients who were assigned. Then over time, we gain information about how effective different treatments are. And there's reason to believe that we can identify the best one and from then on assign patients only to the best one. Okay, but firstly, is that even true? Can we ever be sure which treatment is best, however much information we've had? The answer to this will typically be no, we cannot be absolutely sure. We can have increasing confidence that one or the other is better, but we'll never be absolutely sure. And then that leads on to the question of, okay, in that case, when should we stop testing and decide that we are sure enough that one option is best and stick to it? Or should we ever stop at all or keep testing forever? And so more broadly, how do we balance the exploration of different treatments versus, by exploitation, I mean assigning all patients to the treatment that we think is best based on the evidence so far. So what's the best trade-off between exploration and exploitation? Okay, so this is firstly a loosely framed question. So let's start by trying to make this a bit more mathematically precise. So here's a mathematical model of the setting we just described. Time proceeds in discrete steps. So now time is going to index the patients who come one after the other into this into our hospital and whom we have to assign to one of different treatments. And for each patient, there is a choice of K actions, K treatments we can assign them to, or we'll use the term arms to define these actions. So there's a choice of K arms available at each time step. And if we decide to play arm I, meaning that we decide to assign the patient to treatment, the patient who came in at time step T to treatment I, then there's a random reward xi that we obtain, xi of t. So here in this setting, reward might be that the patient recovers. or it might be how quickly the patient recovers. So if it's just recovery or not, it's a 0-1 variable. If it's the number of days to recovery, that's random variable which takes values in the natural numbers and so on. So you can have the rewards taking values in different possible sets. The assumption in our models is that these random variables are independent and identically distributed. Okay, so every patient who is assigned to a certain treatment gets the same reward on that treatment. This is a simplifying assumption. In practice, there may be observable features or covariates of the patient. So maybe one treatment is better for younger patients and another is better for older patients, or one's better for men and another for women. But for simplicity, we assume that's not the case. Every treatment acts equally on all patients and is equally good or bad. But there is randomness in how well they respond to the treatment. So this random variable xit is going to pick up that randomness. Okay, so this depends on I, and the dependence on t is the independence and identically distributed is over t. So we'll assume that the rewards come from some distribution mu sub I, and we'll denote the mean of this distribution by mu sub I. Okay, so that's about the rewards on the different arms. We assume that these distributions and means are unknown. That's indeed the challenge in this setting. We don't know, and we want to assign them to the best possible treatment. The objective is to maximize the long-run reward in this setting. So that's what it means to assign the patient to the best treatment. We want to maximize the reward xit by choosing the best possible I. The problem, as stated, is still a bit vague. What do we mean by maximizing the long-run reward? So we'll talk about that a bit more. Let me also talk about this terminology of arms that we are using for actions, and the term multi-arm bandit, which we are using to describe this problem. This terminology comes from slot machines in casinos, where a machine has a choice of different arms to pull, and you pull one of these arms and you get a reward from an unknown distribution, and you have to decide which is the best arm. So that's the type of problem we are looking at. And the problem of assigning patients to treatments is one concrete example of such a problem. I should also add that this particular example we gave has an extra dimension of ethics in the decision making. So if you are not certain which treatment is the best, but you think that treatment A is a lot better than treatment B, there's an ethical dimension to, can you assign a patient to treatment B even though you think it's suboptimal? In most of the problems we look at, we don't worry about that ethical dimension. We are just trying to find the best treatment, and we are free to decide how to experiment. Okay, so that's the setting. Okay, so now let me formulate the problem a bit more precisely. Firstly, there are many ways to formalize the objective of maximizing long-run reward, and here is one. So one objective may be to say, let's look at the long-run average reward. Let's go through this formula slowly. So X here is indexed by I of t. I of t is the action chosen at time step t. It's one of the arms between 1 and k. You choose which arm to play at time step t, and it denotes your choice. So at time step t, you play it, and hence you get the reward corresponding to playing it at time t. That's x it of t. Then you add up all the rewards you get in the first capital T time steps, and you take the average of those. And then, so that's this 1 over T times, this is the average. Then you look at the long-term average, which is the limit as T goes to infinity of this quantity. I've written liminf rather than limit because in general, there's no guarantee that the limit exists. It depends on the strategy you choose. For example, if you play the strategy of playing arm1 once, arm2 twice, arm1 4 times, arm2 8 times, and so on, that strategy will have no limit. Okay, we'll be interested in strategies indeed where this limit exists, but to allow for complete generality, I'm defining this as a limit. And then the goal is to maximize this limit. That's maximizing the long run average. This is one precise problem statement. It turns out that this problem is quite easy to solve. In the setting we have defined of IID rewards on the arms, then this problem is easy to solve. And therefore, this is not the problem we are going to study in the first half of the course. We are going to look at a more difficult problem, and that is to minimize the regret up to any time. So that's the criterion we are going to look at, regret minimization. So to make that precise, let me now define regret. So we define the regret up to time capital T in this way. So we look at the so we are taking here the maximum overall arm. So we are finding the best arm, and we are looking at the strategy which at every time step plays the best arm in expectation, okay, which plays the arm K, which has the maximum expected value. That's the biggest expected reward we could get. And we look at the actual reward we got for playing whatever our strategy played. Our strategy played arm IT at time T, and therefore got random reward XIT. And if this happened to be K, you get exactly the same as the maximum reward. This difference is 0 in expectation, but otherwise the difference is positive and you incur regret. And the amount of regret you incur is how much worse off your arm was than the best. So in the slot machine example, if the best arm gives you a payoff of £100 and you pulled an arm which gave you an average payoff of £20, you get a regret of £80 in this time step. Okay, and then you add up the regret over the first T time steps. And I've rewritten the same thing here, introducing a bit more notation. So mu star is the expected reward of the best arm, and you're subtracting the expected reward of the arm you actually played. And that's your regret in the T time step, and you add up all the regrets over the first capital T time steps. Okay, let me pause a bit so you can make sure you understand the definition of regret. Okay, you might have a question at this point. Why are we taking expectations here? Should we not simply look at the difference between these random variables? And the answer is no. It's no, because what we are trying to do in this problem is to learn which is the best arm. And what we can learn is only the average. We can learn the average payoff, but we cannot learn random fluctuations. By their very nature, they are random, and we shouldn't be trying to learn them. And so regret is defined with respect to what we can learn. If we know what's best in expectation, then we can achieve zero regret according to this definition. But otherwise, if we didn't take expectations, we would achieve some random regret, which is just noise and which could be positive or negative. So this is somehow the natural way to define regret. Okay, and then the objective is going to be to minimize how quickly the regret grows with time. Okay, so let's look at the most naive strategy we could think of. Randomly pick one of the K arms uniformly at random and play it at each time. What happens then? Each arm gives some random reward. A fraction 1 over K of the time you play the best arm, you get regret 0. The rest of the time you play some suboptimal arm and you get a positive regret. So on average, in every time step, you get some constant regret. So the total regret over capital T time steps grows like some constant multiple of T. It grows linearly in T, right? So this is the most naive thing you could do, achieve linear in T regret. Then the first question might be, can we do better than this? Can we come up with a strategy that gives us sublinear regret growing slower than capital T? Okay. And the point is that if you can find any such policy which achieves sublinear regret, then by definition of sublinear, that's saying that the regret up to time t divided by t goes to 0 as t goes to infinity. And this in particular means that by this definition on the previous page, so for this problem here, you are achieving the maximum growth rate of reward. Okay, so any policy which achieves sublinear regret achieves the maximum growth rate of reward with time. And that's why that criterion is somehow quite weak. So sublinear regret just has to grow a tiny bit slower than t. It might grow like t to the 0.99 or t over log t or something like that. And that still maximizes long-run reward. Whereas the problem we are looking at is to minimize the growth rate of RT. And it turns out that though this is quite an easy problem to state, this is surprisingly hard to solve. And that's why we are going to spend the first half of this unit trying to solve some simple examples of this. Okay, so that's the problem. And let me give you the big picture of what we can achieve. It turns out that the best achievable regret scales logarithmically in t. So we can achieve RT that grows as some constant times log t. So we'll first see how to do that, and then we'll look at how to achieve the best possible constant c. And in fact, that's quite hard, and we won't quite achieve that with the policies we look at in this course. Okay, so what we are going to look at is what kind of, so how to achieve logarithmic scaling and how to achieve a fairly good constant c here, though maybe a bit short of optimal. Okay, so that's what we study in the first half of the course. Okay, so before we go on to studying policies for regret minimization, we need to learn some probability inequalities because we are going to be looking at sums of random variables and we want to be able to characterize the behavior of these sums. The simplest inequality we have is known as Markov's inequality, and it applies to non-negative random variables with finite means. And if x is one such random variable, it says that for any positive constant c, the probability that the random variable x takes a value bigger than c can be bounded in this way. It's bounded above by the mean divided by c. There's a formal proof of this inequality in your lecture notes. I'm not going to do that now, but let me give you an intuitive explanation of why this inequality holds. So there are 30 people signed up for this course. Let's say the average weight of the person on this course is 60 kilos. And I want to ask you the question, how many people are there signed up for this course who weigh more than 90 kilos? What's the best bound you can give me on this number? Let me repeat that. So there are 30 people signed up for this course whose average weight is 60 kilos. So how many people on this course weigh more than 90 kilos? I'll let you think about that a bit. Okay, hopefully you have come up with the answer that there can be no more than 20 such people, and the reasoning is the following. If there are 30 people whose average weight is 60 kilos, then all the weights add up to 30 times 60, which is 1800 kilos. And nobody can have a negative weight. So the number of people who weigh 90 kilos or more can be at most 20 because that adds up to 1800 already, and the rest have to add up to something non-negative. Okay, that's maybe a little bit unrealistic. Nobody is going to have weights of 10 kilos or less. But if I told you what the minimum weight was as well, you could get much better bounds. But if all you can assume is that weights are non-negative, this is the best bound you can get. And that's exactly what Markov's inequality is saying. So this is one of the most elementary probability inequalities. Let's look at a slightly more refined one. This is due to Chebyshev. And again, we consider a random variable x. Now, this doesn't have to be non-negative, but we assume it has a finite mean ex and a finite variance denoted by var x. And now for a constant c positive, we want to ask, what's the probability that x deviates from its mean by at least this amount c? Okay. And for this, we have the bound that the probability of a deviation of size c from the mean is bounded above by the variance over c squared. Where does this inequality come from? This is actually an easy consequence of Markov's inequality, and you can see that simply by applying Markov's inequality to this new random variable x minus its mean whole squared. Now this random variable is positive, and its expectation is the variance of x. So that gives you this bound. Okay, and yet another inequality, and this versions of this inequality were independently obtained by Chernoff and Bernstein, and it goes by both these names. So again, x is a random variable, could be negative or positive or both. And now we are going to assume that it has finite moment generating function. Recall that this is the definition of the moment generating function. So we first compute e to the theta x, which is another random variable, and take the expectation of that random variable. And let's assume that this is finite for all theta. This is quite a strong assumption, and in fact, we don't need it. It's enough if it's finite in a neighborhood of the origin, but I'll make the stronger assumption. Okay, so if we assume this, then we can get a bound on the probability that the random variable x takes a value bigger than c, and this bound is obtained by taking the minimum of this quantity, e to the minus theta c times the moment generating function. We compute the minimum over all theta positive. More precisely, it's the infimum. And I assume you all know the difference between infimum and minimum, but if you don't know, you just treat them as synonymous. So it's just whenever I write inf, read it as minimum, and whenever I write sup, read it as maximum. There's not much loss of generality there. Okay, so this is the bound for x exceeding c, and you can get a similar bound for x being smaller than c. So you can get a bound on the probability that x takes very large values or that x takes very small values, depending on what's of interest to you. And how do we, where do these bounds come from? They come from Markov's inequality as well. And you simply have to apply Markov's inequality to this new random variable y equals e to the theta x. Okay, and proofs of these things are again in your lecture notes, so I won't go through them here. Good. So there's one more inequality we are going to look at, and this is the one we'll use most widely in this course, though the others are also important. Okay, so the other inequalities we looked at required you to know about the distribution of the random variable x. So you needed to know its mean or its mean and variance or its moment generating function from which you can calculate the mean and variance. So they required different amounts of knowledge about the random variable. And since we are applying these inequalities to multi-arm bandit problems, in such problems, we typically know very little about the distribution. We don't know what part of the difficulty is, that we don't know the distribution of the arm. That's why we are trying to decide which arm to play. And so these inequalities are not that useful directly. Instead, Hoeffding's inequality doesn't require you to know the distribution of the random variables, but it does make a strong assumption in a different sense. It assumes that they are bounded. They cannot take values arbitrarily large or large positive or large negative values, that they take values in some bounded set. And without loss of generality, we are going to take that set to be the interval 0 to 1, the closed interval 0 to 1. It's easy to generalize this to some other interval, but you need to know this interval in advance, but you don't need to know how x is distributed within that interval. Okay, one other difference. So I stated these inequalities for individual random variables. You can easily extend these to sums of IID random variables, and that's how we'll use them in applications. In the case of Hoeffding's inequality, it's most natural to directly go to these sums of random variables. So that's how I'm going to state it. The way it's stated, it looks like you need to know the mean. Okay, we'll come to that. So we have a sequence of IID random variables taking values in a bounded interval 0, 1. And let's say the mean is denoted by mu. Then the inequality says that the sum of the first n random variables. Now, by the law of large numbers, you expect this is close to n mu. And we want to ask how likely is it to deviate from its expected value of n mu. And we are looking of deviations of size proportional to n. So we want to ask how likely is it to deviate by the amount nt, where t is a fixed positive constant. Okay. And Hoeffding's inequality tells us that the probability of seeing a deviation as big as this decays exponentially in n, the number of observations, and the decay rate is e to the minus 2nt squared. So it decays. This is the kind of decay you expect of a Gaussian or normal random variable. And it says that bounded random variables, the sum of bounded random variables decays from their mean in much the same way that the Gaussian does. So this is also sometimes called a sub-Gaussian inequality. Okay, I hope that's the statement of the theorem, and I hope the statement is completely clear. So I'll wait a bit to make sure that you fully understand the statement. Okay, so now that the statement is clear, we are going to move on to the proof. We'll do most of the proof in the next lecture, but I wanted to just outline the first step of the proof. The idea is that it follows by applying the Chernoff or Bernstein bound to a bound on the moment generating function of x1 or any of the xi's, because they are all identically distributed. Okay. And this is the lemma. So this lemma is also due to Hoeffding, and this lemma states that if you have a random variable x with mean mu and confined to this bounded interval 0, 1, then the moment generating function of the centered random variable x minus mu is bounded. For any theta, the moment generating function is bounded by this function e to the theta squared over 8. Okay. And because the Chernoff bound gives us a bound on the probability in terms of the moment generating function, we can use this bound on the moment generating function to get a bound on the probability. And that proof again is in your lecture notes. I won't go over that, but I will do a proof of Hoeffding's lemma in the next lecture. Okay, so let's stop here now.